see you all. I hope this will go well. It wasn't like well prepared. I want this to be way more spontaneous so I can do it more often. So I'll have Tiram, George, joining me, kind of interacting with me. So he's like your voice on stage.
Exactly.
Do we have the recording on?
Are you going to do it? Recording?
Can someone confirm? Yeah, I just want to make sure we have the recording on. I think it will be like easygoing. See how it goes. Yeah, Jester. So here's the only slide for this one. Kind of explaining what I'm going to do, more or less. I'm going to go briefly over some prerequisites. I don't think that would be enough for someone who doesn't have the knowledge, but perhaps like in the recording, when you can slow down and go and look up stuff, and you can get from this whatever you need in order to understand the rest. So some brief going over what various block statuses consensus processing engine has throughout a few stages. And I'll describe briefly the block processing pipeline we have, how consensus is built in layers, sort of. Then a very brief UTXO model overview, so that we don't lose people who need this reminder. And then closer to what we actually want to do is speaking about UTXO state, what the virtual block is, what the think block is, how we manage chain-based DAG ordering, and all like kind of a background. I'll try my best at drawing through a board I'll share on my screen, and using my phone and a pen to draw. And then hopefully we go through the main components of the code, like the virtual and UTXO state processing, actually go through the code, how the algorithm should look like, do our best to understand. And our goal is the sanity checks mean that if I do my job well enough, if I explain the processing well enough, we should be able to answer these 4 points, and everyone who followed should be able to understand these kind of cryptic messages at the bottom. So I'm not going to share my video all the time. I'll just put the screen on for now. George, is the quality good? Is it like smooth?
For the moment, it was nice, but are you sharing your screen? I don't see it.
Okay, I guess so. Maybe you have connectivity issues. I don't know.
Oh, this can be.
I don't hear you well, but I hope everyone hears me well.
I do hear you well.
Audio a little choppy. JWJ, is the audio less good than? Okay, now you can hear me well. Okay. You see slides. You see only one slide. You hear okay. Okay, so let's try going with this. So we should get back to this slide to see that we're doing well enough. And if okay, like if something. If you don't hear me well, and I just keep talking, so someone should get on stage who has the privileges and let me know. Thank you. So I'll be going through this slide. And using this board, I'll do a test. And we'll go through code in case you wondered. Things like this. Okay, so I'll start with first thing. I think that would be chain-based DAG ordering, maybe. So the way I look at it is understanding that a DAG, we have a DAG, some kind of DAG, and we have this rule where each each block has this magic function which allows it to select a specific parent. So the DAG structure, unlike a chain or a blockchain, which actually created a tree structure, since each block points at one specific parent, but you can have forks, so it's not exactly a chain, but a tree. And Bitcoin, you have the longest chain being set as the main chain or the only chain that counts. In our case, a block can have multiple parents, but we have a magic function that allows us to select a specific a parent from each block. This function is called GhostDAG, and I'm only drawing the selected. Parent for a specific chain of blocks. So we have a special block called virtual, and it's not an actually mined block already. It's a block that virtually exists. It points at all DAG tips, all the blocks that no one else pointed at yet, and it applies the same function for selecting its selected parent. So we have this virtual block, and we call the block the tip which the virtual block selects as a selected parent. We call it the sync block. So by creating this, using this GhostDAG function for selecting a parent for each block, you kind of get, if you start from the virtual block, you get a chain, a selected chain. And that's what we call the virtual selected parent chain, or names like that, which are used frequently also in the RPC API. And this chain is a chain that stabilizes one of the guarantees GhostDAG protocol as a secure protocol provides is that the chain selected by GhostDAG stabilizes in the sense that only mutates at the suffix. Like you have this large, for instance, all this part of the chain is already stable, and you can have the chain switching to this block eventually, maybe soon, but there's frequent changes at the tips, but the change mostly stabilizes. And if we find a way to order the DAG through this chain, where the chain dictates the ordering, so we also get a stable ordering of the DAG, that's what gives us security. Once the ordering is stable, we know exactly what transactions were accepted in that section of the DAG, which is already stable. And the only changes happen near the tips, which we're still converging on. So usually I draw, instead of drawing like instead of drawing this full DAG of blocks where you see all the relationships, I often will do chain, and I'll describe layers going like this. This would be what we call, like if this is block B, so we would have, if this would be, so we call this area marked in blue the merge set of B, meaning it's all the blocks that are in the past of B, meaning they are reachable through parent references by B, but are not in the past of the selected parent of B. So this one here is like the B.sp, the selected parent of B. So by selecting this block, let's call it A, as B's selected parent, B kind of accepts the point of view and the worldview of A, including its ordering and UTXO state. And then it adds this new layer, which we call the merge set of B, to the ordering, after everything that came from A. So that's the merge set of B. So by using these merge sets, you can see that, merge set B equals the past of B minus the past of the selected parent of B. And by using this merge set, you can see that we kind of order the DAG in layers by the chain. And because the chain is stabilizing, the DAG ordered by it, dictated by it, is also stabilized. And that's essentially the security. Okay, so for this talk, we don't need to understand Ghost DAG at all. Just need to assume that it has this magic property where the chain stabilizes. And all we need now as our utility is this chain. And this chain is how we process UTXO state and how we manage reorgs. How the virtual selects its parents and selected parent. That's all we need. We don't need Ghost. We'll use Ghost DAG only in one specific place where the Coinbase transaction rewards go to blue blocks and not to red blocks. For red blocks, the merging chain block can gets the reward, and that's the only place where we'll use more than the selected chain. Like Ghost DAG provides not only the chain selection, but also the coloring, what we call blue and red blocks. So that's used only in one very particular place. But mostly for everything related to UTXO state management, you look at the chain. So we covered shortly what virtual is, what the sink is. The sink is the virtual selected parent, and chain-based DAG ordering.
Michael, can you show the board again?
Yeah.
Just point at the sink so everyone is aware of the block on your design.
Okay. Yeah. Let's do it like this. So this is a sink.
Yeah. Okay.
Yeah, in graph theory, you usually have for a graph, like a directed graph has a source, kind of a vertex or a block where everyone is pointing out and doesn't point at anyone else, and the sink, which is the opposite of that. So the closest name we got to was sink. Yeah, it's kind of known.
Yes, we just need to remember that the virtual is not an existing block yet, but the sink is an existing block, which is the candidate to be the selected parent of the virtual.
Right. Here I added dashed lines, so now virtual is clearly not real.
Great.
Okay. Now you do QE. Okay, we'll get back to more. I think we'll get back to more slides in a second. But let's speak about. Okay, so I think block status would be the next natural thing to talk about. I can still use this picture for that. So, in a blockchain, you would have at most 3. When I say block status, it means like we looked at this block or at the header, and we already have conclusions. Like if we only saw the header and we validated the header structure is all fine, which is not the topic of this call, so I'm not going to go into header processing at all. But once the header is validated, we say status header only valid. Okay, so that's the first stage. You already proved proof of work is okay, and you're pointing at parents, and you have the right blue work and blue score and DA score and everything in the header structure, almost everything. But everything that's related to the header structuring of the DAG is already validated. That's status header only validated. And then we have another status. So I'll just go to the code for a second so we can look at this. So a block can be header only. It can be invalid. At any stage, we can conclude that it's invalid. It can, like, invalid can come after being header validated, but then something in the body seems wrong. So in a blockchain, you would have header only. Maybe you'll have valid, including UTXO state, and invalid. You'll have 3 states. Essentially, a block in a blockchain, you either, so header only is just a temporary kind of status. So I'm not going to use that. So you're either valid or invalid, because fully valid or fully invalid, because we look at the block and we check the header properties. We look at all the fields, and we check the transactions are okay, and we compute the UTXO state of the parent of that block in a blockchain, and then we verify all transactions in it are valid in that UTXO context, which, saying the words UTXO context maybe not everyone will understand them. So we'll get to that shortly. I'll go briefly over the concept of UTXOs and in UTXO context, what I mean when I say UTXO context, UTXO point of view, same thing. But you're either valid or you're invalid. If some transaction is illegal in the context, meaning it's using a UTXO input that doesn't exist in the UTXO set, so the whole block is rejected as invalid. That's what you do in blockchain. Emphasizing, not in Kaspa. Why do we do anything different? So why do we have these additional 3 statuses? So I'll just point out again in the here, if we have this DAG structure, assume we already computed the UTXO state of sync and virtual, so we're kind of up there, and then a new block arrives pointing down below. Either it was published late or mined not at updated data, so it's kind of off. So, and it happens to include a new transaction. So we're a DAG, right? We like to be inclusive. We like to be accepting stuff. So we look at this block and we want to look at this transaction. But if we would need to compute the UTXO state of this block, we would need to roll back. Like the situation, our state of UTXO. We'll need to go back here, and then verify that this block is valid from his point of view, because he supposedly didn't know about the future. So we can't blame him for transactions spent at him. So we need to verify him according to his view. So we would go back, and it would be costly. So that can create like a very cheap. Us being so accepting creates a very cheap attack vector where you can just get this block, lazy block, which is 30 minutes back, and the whole chain needs to be reversed, and you need to verify that special kid according to his conditions. And we don't want to do that. So, and we also don't need to do that, because essentially this block is not claiming to be the sink or something like that. It can't be the sink because it's very late published. It's not going to have sufficient blue work to be a selected on the selected chain. So we don't really need to know his point of view in order to verify it. It can still be validly structured. It can have the correct header fields and all that, but we don't want to UTXO validate it. So that's exactly what we do in block status. So essentially, after the block is, after we look at the transactions of the block and we verify them locally, we look at, get to that soon, but there are some checks we can do without a UTXO context, without knowing what funds are available. We can just check the structure is okay of transactions. So once we pass that point, we declare this block as valid, but UTXO pending verification, meaning we don't know if it's a chain block, and we don't need to know because it's not a candidate for being a chain block yet. And then we have two new statuses as a result. So if this block or any other block does become a candidate for being on the selected chain, because the chain it's within is winning the block race or doing a reorg. So at that point, we will check the UTXO state of that block, because it's worth it. It's proving enough proof of work for us to check its real UTXO state. So once we have such a candidate, we look at it. And then you can have two different outcomes. One can be that it is UTXO valid and it can be a chain block, which dictates the ordering in the UTXO state of the DAG, or it can be invalid in the UTXO state, and then we declare it as disqualified from chain. But I emphasize that this block is still valid structurally. It belongs to the DAG. It will be broadcasted to peers. It can be mined over. It can get it can even get a reward. It's just simply not going to be a chain block. Normally, no one creates such blocks, but it is possible, and it's a distinction. It's a clever idea. I would blame Ori for it, Ori and Jonathan for this design. Clever idea for avoiding what you don't need to do, avoiding computations you don't need. And that's basically, okay, my pass on the concept of block status and why we have more than just two states, but like four.
So typically, this kind of block could be a candidate to be a red block, right?
Yeah, if it can be, usually it would be a red block. It would be but if someone published wasn't publishing this block late, but publishing it like on time, but still mail formed, like it wasn't. It has some field that isn't UTXO valid. Like we'll see as we go what UTXO validness means. But if the candidate to being the sink, for instance, turned out to have invalid UTXO state, so this virtual will not point at the sink now, but it might point at it in a few seconds once other blocks like precede it and have more blue work. So there's a sink, and now we can look at this block and include it as an additional parent, because it's not the selected parent anymore and it doesn't dictate the UTXO state, which we can't follow because it's invalid in terms of that. So we can't allow it being a selected parent. And we want to always keep the rule where the selected parent is the one with the most blue work. So if such a block does arrive, we simply avoid it. We don't even point at it as a parent, and we move on, and then eventually it can be added to the virtual past later once it's not a chain candidate. That's more part of the algorithm we might look at. Okay, is that clear?
Yes. Seems good.
Yeah. Okay, so now we can look at so if I look at the code base, very briefly say that most of the everything related to consensus is under consensus. So Rust has a concept of crates. A crate is like a software package, and you can have subcrates. So if you look at a folder, it will always have an SLC, which includes a hierarchy of Rust code files, where each code file is kind of a module. And here, besides SLC, we have also subcrates. So the most important subcrate under consensus is core. Core is where we have all the data structures that consensus needs. The basic data structures, the header, a block, transactions. And you have the consensus API, which is like a huge kind of big interface which other part of the application get. And we have many basic utility functions, like whatever is needed for hashing the header, a transaction, a sig hash, LL management, UTXO related stuff, which we'll get to. More or less, a lot of basically a bunch of data structures, what we call what one would call the model, like a consensus data model. So the header is this is like a cached hash. So you have a version, you have parents. Ignore the double vector for now. You have the hash Merkle root, which is the Merkle root for all transactions in this block. You have the Merkle root for all the transactions accepted by this block from its merge set. And here one might notice that this root uses transaction IDs, and this one uses transaction hashes. It's a very important distinction. Hopefully I get to it, but it's subtle. Then you have a UTXO commitment, so these two fields are part of UTXO state. So they're not validated header processing stages, but only as UTXO state processing. Only when a block becomes a chain candidate, we verify these. The UTXO commitment actually folds in it the entire UTXO set cryptographically committed to like what this block was thinking the full UTXO set looks like. Kind of non-trivial to think how you maintain this commitment efficiently. How can you, for each header, hold the entire commitment to the entire UTXO set, despite frequent changes? So we'll get to that. Timestamp bits, which determine the difficulty, nonce, DAs scope, those scope, and all this. So this is the header. So I wanted to go very briefly over transaction because just to understand what UTXOs are, very basically. So the thing to notice is that a transaction in Kaspa, any transaction in the UTXO model, in a system which supports UTXO-based system. So you have a version for the transaction, okay? You have inputs, naturally, and outputs. All the rest is not required, like for now, for this discussion. But essentially, the transaction is a set of inputs and a set of outputs. You can all relate to that. So the outputs hold what you would expect them to hold. How much value goes to this output, and to what address. It's the script public key, which would be the owner for this value from now on. But the inputs lack some data; they're not full. So the input holds this weird thing called transaction out point, a signature script, essentially the signature, and these two not critical to discuss now things. So the signature is obvious. What is the previous out point? So transaction out point is a transaction ID and an index. So essentially, this transaction is telling us my first input comes from the output of this specific transaction, transaction ID, and I'm using the output of that transaction at this index. Like if it was output number 1, this index will be 0, like indicating the first output. If it's output number 2, the index will be 1. So I'm essentially not telling you what the input amounts are, who's the owner. It's all like only telling you kind of an ID of where I'm taking this Kaspa value from. So how does this work? Essentially, in order for the node to verify a transaction coming to it, doesn't need to know the structure of previous transactions. It doesn't need to know history. All it needs to know is the outputs are available, meaning I need to know that the transaction input is spending an unspent previous transaction output. Unspent transaction output is what we know as UTXO, unspent transaction output. And essentially, the ID, the key for this UTXO entry is the transaction that created it and the index of the output. So that's a unique ID for this output. And the node holds this thing as inside the UTXO set. And then you have the UTXO entry. For each transaction output, the node has a special UTXO entry holding the amount, which would be the value of that output. The script public key we saw at the output, block DA score, where it got accepted to the DAG, and whether it came from a Coinbase transaction or not. So essentially, the process is like this. You get the transaction, you look at the input, you have outpoint, you go to the UTXO set, the storage of this node, which has a full UTXO set, you look at the key coming from transaction outpoint, and if you find the UTXO entry, that's what you know. So you know how much money it has and who's the owner. And then you verify that the signature is legally allowed to release the funds encoded by this ID, and you kind of accept the transaction. So that's more or less a brief about transactions and UTXOs and stuff like that, which is obviously essential for this conversation. Is this clear?
For me, it's absolutely clear, but I don't know for the audience. Any question?
Yeah. So if you can look at the chat while I'm getting the next, see if anyone is complaining badly. I'll pick on a camera just to say hello to everyone.
I think it's okay.
Okay. So I was starting to go over the code structure briefly. So I mentioned call. Then there's a bunch of other stuff, including amazing out-of-node infrastructure, wallet, WASM, APIs, and all that. RPC layers here is like a whole world of architecture George knows very well. And you have under protocol all the peer-to-peer logic, peer-to-peer infrastructure, peer-to-peer flows. Mining is where you find everything related to the mempool and the building a block template, which we should touch if we don't happen to get to the morning. And crypto is everything crypto related, mostly written by Elichai a year and a half ago at the beginning of the Rust rewrite effort. he's like an applied cryptographer, so he's a good source of authority in this. So that's everything related to hashes and mu hash, which is related to the UTXO commitment I mentioned, which is has unique properties of a hash function, which allows it to be easily updated by new items and removed items. And here you also have the transaction script engine, which was written by Discord. People know him by Haunted Cook. He's also named Tomer. So that's under crypto. But I'll focus on consensus. And I went briefly over core. And now the main consensus engine is under this, consensus SRC. So I wanted to say something fast about the pipeline. So here we have like basically a storage layer, a series of stores and services, and consensus is the storage function, storage object, which holds like a bunch of stores. And then a services function, services object. And so that's under the model. And then we have processes, which are like various services or logical components of the system, like a reachability layer, management of the point proof, logic of ghost DAG, what we call like incremental ghost DAG, which is not a straightforward translation from the paper, and transaction validation, everything related to transaction validation, and a few other logical processes used in the system. Then you have the pipeline. So I'm going to mostly go through the pipeline. Pipeline is a parallel structure. I would think about it as a so we have header processing. Think about it as a unit. We have body, virtual, and pruning. So this is like think of a pipeline or I don't know, a manufacturing place where there's like each person has a job and they pass items through them, and everything is processed in parallel, because at the time you have header processed, it moves on to the body processor, and other headers can be processed by the header processor, and so on. And each has different dynamics. And it's all related to the block status I mentioned before. So it's a pipeline. You first validate the header, and then validate the body, and then it goes into the virtual UTXO state processing, and sometimes it's computed, sometimes not, depending on if it's a chain candidate, like I mentioned. And then finally you have a stage where things are pruned. Pruning is a process which is triggered like once a day currently. It's not like an ongoing thing. And each of these stations has unique properties that allow more parallelism within them. Like header validation, if we look at the previous slide, headers that are parallel to each other, in an anticon, we call it the anticon. The anticon of a block is all the blocks which are not reachable from it, or it's not reachable from them. So all the parallel blocks, and these parallel blocks have no dependency on this block. So by definition, they can be validated in parallel. So if you think, so it's a kind of interesting property where you increase, you can increase the BPS of a system, say to 10, like we do in testnet 11, and more blocks will be created in parallel due to the natural latency of peer-to-peer network has natural latency, say close to a second. So on 10 BPS, you'll have 5 or 10 blocks parallel, and that allows you to utilize your compute resources more efficiently, because these parallel blocks can be verified in parallel. So if you have like a 10-core CPU or 30 or 16 cores, the system benefits from this parallelism and its performance, which is a very nice property. Same goes for body processing. body processing is also can be done parallel to all parallel blocks. Virtual processing is a different creature. For virtual, if I go back to the previous slide, so we kind of, if I look at the right here, when so we can't do chain blocks are by definition sequential. They're one after the other, so we can't compute them, the state of a chain block, the UTXO state of a chain block in parallel. But we can use parallelism in other places where when we go over the merge set for each block, we have a block here, if it has like 50 transactions or 200 transactions, we can verify them all in parallel, and that's where we use parallelism for virtual UTXO state processing. So at each point in the processing pipeline, we try and exploit the correct way of parallelizing things, and all this performance effort is like 10 bps. testnet 11 wouldn't work properly without these. Like you need to use and you have multiple CPUs on any commodity computer today, so that's like a very basic resource, and we make heavy use of it. And we couldn't speak about a 10 bps system without multi-core parallelism exploited to the maximum. Yeah. So that's the pipeline. So okay, we made it through the brief. I hope it was brief enough. So now I think we'll mostly. Are we good, George? Can we move on to now? It's going to be more through using everything we went through and understanding how the UTXO state processor works, which is very kind of heavy stuff. I hope you all take from it and can, and we'll do our best.
It's a lot of information, of course, so I can imagine that it's a lot of information at once, so I can imagine for the beginners it's quite difficult.
So that's why it's good for the recording, that
yes,
someone who wants to follow. So I think we went through everything one needs to know. So
yeah, basically I think so.
A lot to digest, but yeah. So we're mostly going to focus now on this pipeline, virtual processor. So if you know Rust, so I'll be more specific about the pipeline. Just the processors are we use normal threads to initiate the pipeline, and then we use Rion extensively in different ways. Like when you set up consensus, it's gonna look something like this. You have a header processor and a block body processor and a virtual state processor, and then processor, and they get these thread pools. They get processor channels where they can communicate with each other through beam channels, and thread pools coming from Rion. And when you initiate consensus, you run for each processor a worker and a dedicated thread. And this is like the consensus engine, like a skeleton. And if you look at this worker, it's going to kind of loop over a message channel receiver, which sends it block processing tasks. And it's going to register the task in some task manager, which ensures that DAG dependencies are processed in the right order. That if you have dependencies already queued for processing, if your parent is queued for processing, you're going to be actually queued for processing only once your parents are complete. Only once the parent verification is done and they're valid, then we'll queue you. So there's a task manager, which is sensitive to DAG structure. And it's used both, it's what we call here depth manager, and it's used both for header processing and block body processing. And then there's a mechanism for queuing the block, and then eventually you start processing it. And you validate the header, and then you commit the header once it's valid to the stores and to the database and everything related to that. So you have this processor, you have the body processor, and then the virtual processor. So we're going to focus on this one. And here it's going to start getting harder to follow, but let's try.
So this one is not going to benefit directly from parallelism, right? Because there is only one virtual in the system.
Right. So first of all, you have what I would call concurrency, where headers can be processed in parallel to the virtual doing its thing. But like I mentioned, we use, if you want to see where we use parallelism in virtual, you would track usages of the thread pool. And you would see, you know this, but you would see that we validate the blocks. That's what we validate transactions in parallel. So we kind of we use the parallel iterator, and we validate each transaction in the UTXO context in parallel. And we rely on the fact that, as this comment says, we can do this in parallel without complication, since block body validation already ensures that all transactions within each block are independent. So we have a previous process running and verifying as part of block validness that transactions are independent, which is why we can exploit parallelism here. And this is very significant. Like when the DAG is not loaded, so it's not a bottleneck anyway. And if you start having tens of transactions per block, this is enough to use the resources you have. Okay, so I want to write like kind of a pseudocode for our own result virtual. So essentially, we have we're given a set of we have a tips. Imagine they have data, and we have so I don't really need like let's do it like this, more like a comment. Okay, so how would the logic be? So we have inputs to this. We have the tips, the current state of the DAG, which structurally, that's the tips of the DAG. And we have what we call virtual state. Something encoding in it like what virtual was up to now. Like if the network just started, so virtual would be very simple object looking at Genesis, for instance. But so we always have this previous virtual state, and now we have an updated set of tips, which include at least one block that the previous virtual state wasn't aware of yet. So now we have a new block or more, or many, and we want to compute the new, and we want output to be as a new virtual state. and UTXO set changes. Like not only UTXO set changes, but for simplification now, I'm just going to focus on that. So we want to know how the new virtual looks like, and what are the UTXO set changes we need to apply to the database in order to update the UTXO set with the new state of this node. The UTXO set, it's what we call it the virtual UTXO set. The UTXO set associated with the virtual block, and that's essentially the money or the UTXO state of the system. How many coins each address has, and with what amounts, up to date with this exact DAG fully processed. And this information changes frequently at 1 BPS. You have new transactions mutating the state. The UTXO set slightly every block, every second. But the changes, the UTXO set, you can imagine, can be several gigabytes on the disk. But the changes made by specific change are usually like small in size. Extract 200 UTXOs and add 300 new ones. Like the change that this processing would be, the outcome of this processing would be a change to UTXO set reflecting the new state of money, the new state of Kaspa. When I mean new virtual state, I'm the virtual block and information related to that special block. So that's going to be like kind of a header in a sense. So as part of the previous virtual state, you let's call this previous virtual state, or just P. This will be new. So P will have some kind of what we call the previous sync would be P dot selected parent. That's the previous sync, and our goal is to look at the new tips and find the new sync first. While we do that, we need to compute all the new chain blocks from the previous sync to this new sync, and we have to validate the UTXO state of all of them. And we, along doing this, we accumulate the UTXO set changes. Like we keep a structure which accumulates all the UTXO set changes from the previous state to the new state. And when we get, and then, so we first step. So step 1. Yeah, tips don't point at virtual. Virtual always points at the latest tips. Essentially, not all the tips. You'll see there are rules, but eventually it points at a subset of the tips at least. Usually all of them, but not always. Okay, so step 1, run and find the new sync, computing UTXO states along the updated chain. Then once you have the new sync, it's called pick virtual parent. So you select the additional. So usually, almost always, the sync would be a block that is in tips naturally. Exceptions will happen only if there's disqualified block, but we don't have to think about that too often. It's just important to know. But essentially, the sync would be one of the tips, and then the remaining tips should be the remaining parents of this of the virtual block. So select So select an additional parent. And this is not always all the remaining tips, because the header structure has a limit of the maximum number of parents. We don't want the header to be unbounded in size. So there's a limit to the number of parents a single header can point at. So if the number of tips happens to be very large for some reason, something is usually indication of an unhealthy network. So the virtual algorithm will not choose all of them as parents, but only a subset of them, using randomness, so that the network converges, because different miners will randomly choose other different parents, and eventually everything will be merged. So select additional parents. Then you compute the new virtual state from with these parents. You literally like build the header, assuming these parents. Now you build the header. You define the difficulty based on the parents you just selected and the blue score and all. You fill up the header information to compute the new virtual state, and then you commit. You update like locally in the database what the new virtual looks like. Commit virtual. Like up to now, all the computation was local. We haven't like updated any database. Like if other components of the node would query a virtual state during steps 1 to 3, they'd still get the previous state. It's only when we commit, we like apply in a batch, like meaning the DB, we do it in a batch step where either all accepted is, or like if the node crashes exactly then, the state will be consistent because we do it like in one update. So you commit the virtual state to DB plus C. You also apply the UTXO set changes along this update, and that's essentially you're done with updating the new virtual and the new UTXO set state. Yeah, so that's the overview of what we're going to look at, which is a lot of this file and UTXO validation file here. Are we good?
We have the program, perfect.
Okay, so now I'm gonna walk through the code. Okay, I'll try like highlighting like various things which I think might be cool in terms of Rust, maybe design. Let's get to it. So essentially, this is all virtual. It's going to do more or less, not more or less. It's going to do exactly what we described here, and it's the top level structure is very looks very much like that. We start from getting the previous state. We lock the virtual store for read. We don't apply it writing semantics. So it's an upgradable read. No one else is going to compete with us. We're the only ones who attempt at writing eventually to the virtual stores. But we do a read here. Eventually, when we commit, we'll upgrade this read lock to a write lock and apply the change. So we have prev state and we have tips. Okay, there's some kind of filtering here which is irrelevant, out of our scope, I'd say. And like I've done here before, extract from previous state the selected parent. Selected parent is part of the Ghost DAG data because Ghost DAG is our oracle for selecting a parent, so that's how the data is stored. And we start with the set of changes C. So let me just get this here closer. So we have the tips, we have the previous virtual state and the previous sync. We have and we want to build the new virtual state, and the UTXO set changes. C and C as well would be the accumulated diff. So the accumulated diff, you would expect it to be starting from an empty difference. Yeah, I think this will be uploaded. It's recorded, so hopefully, hopefully it should be uploaded. Okay, so for explaining this this line, I think I need to go back to the. First, I need to go to explain what a UTXO diff is, and I need to explain why we reverse it.
Michael, can you magnify a little bit the code? Oh, perfect.
Okay, so I was saying I need to go to explain what a UTXO diff is first. So now we're back at core under UTXO. So UTXO collection is simply a map from if we would hold the UTXO collection in memory, it would be a hash map from transaction out point. As you can see, is a key uniquely identified by the transaction ID that output came from and the index. So that's a unique identifier for an output, a UTXO. And the value would be the UTXO entry, amount, SPK, and the rest. Eventually, now I'll add this abstraction we have. Soon I'll fully explain it. So we have an abstraction for UTXO view. Essentially, it queries whether some entry exists. So it provides an out point as a key, and it receives an optional UTXO entry. Option means it can be an empty. The result can be none, wasn't found, or some, it has an entry. So essentially, there's a UTXO view, UTXO set view, and you can query it for a specific key. Very simple. And like I mentioned before, like the UTXO collection is like in memory, but the same UTXO view would be implemented for the database as well. Like if I go here, if we go to consensus model stores, you'll see that we implement the UTXO view for the UTXO set store. That's like the underlying store. Okay. Then you have UTXO diff. Without going into complicated concepts, it's a very simple thing. It's saying these UTXOs were added and these were removed. It's a difference. If you take the base view and you apply this diff, you get like, conceptually, you get another UTXO view. So that would be a diff. Okay, I'll get back to I'll explain it more as we go. I'm aware that it's not fully clear yet and why we need it. So I think I should go back to the whiteboard for a moment.
I think Node would like to ask a question.
Okay.
Where is he?
Is it like a request to speak?
Yes.
I don't see it now. Maybe.
Okay. Perhaps he changed his mind. I don't know. I don't see him anymore.
Okay.
Sorry.
So I want to Shall we see my pen? Yeah. So I want to explain like what a reorg looks like. Essentially, we might be tracking a reorg. We had like a virtual pointing at some sink, and there's additional blocks. So the virtual has more like a merge set. And maybe the new sink is going to be like a block here. Now there's a new block which has higher blue work, so we want to compute the chain based on him. We want to recompute. So our UTXO state eventually actually like advanced. We had this we had the UTXO state here, and then we went here, and then we applied also the merge set of the sink, the previous sink, to the virtual UTXO set. And when we want to go, now we need to do this reorg, where we go back. We reverse the UTXO state we already computed from this sink, take it back, and then we go. So we want to do this like going back here, going back to here, and then we'll compute this, and this, and this, and then the new virtual, which might have more blocks, looking at more blocks, will compute its new state, including the UTXO set state. So eventually we already, because virtual was pointing at a specific sink before, so we already updated the disk, the database with these new. Think of it as maybe there's like some transaction here, and we updated the database, some outputs of it, new unspent transaction outputs. Now we need to roll that back. So that's not so easy. If you look only at the transaction, if we hadn't keep any data originally, so we couldn't know how to go back exactly from how do we reverse a transaction, because the transaction doesn't hold the full data, like it doesn't have the UTXO entries used as inputs in its structure. So looking at the transaction alone, it's not a reversible function. Like if you think of applying a transaction to the UTXO set as a function that operates on the state, the UTXO set, and updates and applies a transaction as a change to the state, and the result is a new state, so you don't know how to go back, at least if you don't keep information. So the UTXO diffs purpose is to essentially record these changes so we can roll them back if we need to. So by keeping, for each block, we computed the UTXO state, including virtual, which is a special block, but for this discussion, it's just another block. We keep a UTXO difference of it from its selected parent, meaning we started from the UTXO state context point of view of its selected parent, in this case the sink, the previous sink, and we applied all the transactions we found in the merge set of virtual, all the blocks which are parallel to S, essentially, and we compute the transactions and we apply them to the set, but we keep track of exactly the exact UTXO difference, so that if we need a reorg in a second, or in 2 seconds, or in 10 seconds, we can roll back to the split point. So I call this the split. We roll back up to here. Essentially, we look at the UTXO diffs we already computed and we reverse them. Everything added is now removed, and everything removed is now added. We reverse the picture, and we apply it on the UTXO set view as like a set of a bunch of pending changes, and we go back, and then using these differences, and then when we go back here, we compute the new as we go up, and also memorize the UTXO diffs just in case we need to roll back from that again in the future. So this would explain why when we start the accumulated diff that I named it C here, the UTXO set changes. So we begin by looking at the previous state, the previous virtual, at the UTXO diff of him from the sink, and we reverse that because we're not touching the database yet. We're not touching the UTXO set in the database, but we're memorizing exactly the change from it we should be looking at from now. So we're kind of using the diff, we're kind of looking at a mask which will hide everything that was added previously and will add everything removed previously. So that's what happens when you reverse. Essentially, it's a simple function. Creating a new object with everything removed as add and everything add as removed. So it's a reverse diff. It's a simple idea. Now, I think this might be the point of the point in time where I share like a cool structure. Like I described the abstraction of the UTXO view. So essentially, what I'm saying is there's like a programming challenge here. Be with me on this, George. How do you easily, like many functions you want to write them in a way that they just accept the UTXO view, right? And they don't care exactly if this UTXO view is composed of 700 layers of diffs or whatever. They just want a unified UTXO view where they can query to ask if this UTXO exists or not, right? So the idea of the UTXO view is a trait exactly meant to be abstracting this. And then we have a general form which essentially can be recursively used, and you'll see that soon, where we say this is a composed UTXO view, it's a struct. It has a base UTXO view, and a diff. So the immutable UTXO diff is going to have like a simple added and removed, same as a diff. It's just abstracted. And then this composed UTXO view essentially implements also UTXO view itself. Right? You agree conceptually that this composed UTXO view is also a UTXO view. So how does it do it? The implementation is generic. You can simply look at the diff. If the entry exists in the added set, so we consider this entry to exist. If it's in the removed set, we consider it as removed, and so we return none. And otherwise, we just fall back to the base view. So it's a recursive structure. And essentially, you can compose this in layers over and over. And we do that up to twice. In the code, we actually compose like 2 layers of UTXO diffs. There's like a cool extension method where you can compose. And so that's how you abstract like the idea of UTXO view. So essentially, you can have like when you pass later on, you'll see we passed the UTXO verification method. We pass the UTXO view, a generic one, compile time flattened. So and it can be representing something coming from first the DB, above it a accumulated diff which represents all the changes from the reorg, plus the merge set, specifically a more local diff we'll get to. And they're all composed into one object, and that's how we always try to stay consistent with UTXO views. Which any slight, yeah, any slight like that, it should be clear that this is like the most sensitive place in consensus, probably. So we start with this accumulated diff, and essentially it's going to hold the difference. Think of it as a reverse. Like our baseline view is V, and we added a diff that is reversed that essentially gives us the point of view of sync. And then through our search, the sync search algorithm, we're going to update accumulated diff with the diff of the new sync from the previous virtual state. Essentially, that's what's going to happen. And so like I described, you find the new sink, there's a sink search algorithm, computing UTXO states along the updated chain, and updating this C, accumulated diff structure. Then you select additional parents. You call pick virtual parents. Is it large enough, the text? I can go a little larger.
Okay.
And then we grab a little data, and then we do the calculate and commit virtual state, which is where we take this is folded. Seems like a magic function. So it has the virtual parents, the virtual ghost data, the sink information, the accumulated diff, and we compute the new virtual state, and we commit the virtual state plus the changes. So that's the structure. And then the following things here are a bunch of notations sent now out of the node to the RPC layer. First of all, out of consensus engine, out to the RPC layer. Everything like this. That's what wallets and exchanges and any service provider listens to, the most essential notifications about UTXO changes, acceptance, transaction acceptance, and so on. And so that's like the notification part. But essentially, the computational part is all here. Of course, this is going to be long.
What's the largest depth a reorg can accept?
It can go up to finality in theory.
Oh.
That's essentially where we use the idea of finality. If the reorg goes below the finality point, we reject it, even though the new chain has a high proof of work. I don't think Kaspa mainnet ever a meaningful reorg.
That deep, I don't think so.
Yeah. So meaningful would be even 10 blocks, I doubt. Maybe only under extreme, like some, I don't know. 10 would still be okay, but I don't know about such an event. So it's usually but in 10 BPS you have more frequent reorgs of 10, 20 probably, naturally, because you have 10 blocks a second, so it's gonna happen. So, okay, let's do like hopefully 20 minutes to going into these methods, and then a few more minutes to understand the sanity checks.
So perhaps you should explain finality, the concept. Just in a few words.
Finality is a subjective term, because essentially we say that if the reorg goes deeper than more or less 24 hours worth of chain, we reject it, even though proof of work consensus, like Nakamoto consensus, like Bitcoin, like longest chain rule, is, if you look at it from the theory perspective, it's probabilistic forever, meaning there's always some kind of probability that a new chain will emerge and will roll back the entire Bitcoin or Kaspa history, if you look at it from that pure paper. But in practice, we don't allow reorgs to be too deep in order to support. So the current number is 24 hours. It might be shorter for 10 BPS, because this number affects also the pruning depth and the duration of the pruning period, so how many days each node must hold. If you make finality shorter, you can make so for testnet 11, we keep only like 40 hours of data, and for mainnet, we keep more like 72 hours or even 80 hours. So by shortening finality, you can also, the trade-off is what happens if, in theory, a very deep reorg happens, and finality is a concept that is dependent on the point of view of this local node, because you kind of look at the depth of the reorg. And it depends on the exact, like if the threshold is some number, so there might be a case where for some nodes, finality was already achieved and they're not going to reorg, and some parts of the network might not progress enough and still think the reorg is valid. So anything finality related is like out of the consensus, pure consensus design. And it means that if such an event happens, that's why we say 24 hours are enough for agreeing on a social consensus. Like there's going to be a version or an agreement on what chain we use. And a fast version will be deployed where the chain is forcibly selected to be the one that everyone agrees on. So that's just a natural dynamic. But I'm trying to stay technical here. So finality is like a point where we don't reorg below. Simply that. And it only depends on this hash path. So essentially you can manipulate it very easily in code if you need to. So yeah, there's an RPC mechanism for it, but it's not completely developed, and it's also very sensitive to do that for RPC, so it's not the best idea. Anyway, sync search. So unfold all. Okay. So I'll read the description. Searches for the next valid sync block. The search is performed in the inclusive path of diffs, including the diffs themselves, provided diff is assumed to initially hold the UTXO diff of previous sync from virtual. That's what we saw. It start with the reversed diff. The function returns diff, with diff being the diff is a new sync from previous virtual. In addition to the found sync, the function also returns a queue of additional virtual parent candidates. So I don't know exactly how to do this. What do you think? Should I walk through the main parts? What would you want to know now?
I think yes.
So I think I can jump to UTXO validation. Look at how a validation looks like, and like this is like from the point of view of a single block. So you have like you have the world, the selected parent UTXO view, and you want to calculate the UTXO state for this block. So that's like a local operation. And then we'll go back to the sync search and see how this is used. Is that a good idea?
Yes, makes sense. I think it's good.
So it's pretty fast. There's two main methods here. Calculate UTXO state and verify expected UTXO state. This means like once we calculate the UTXO state, we know the UTXO view of this block. And then we verify that all the header fields that I mentioned earlier match this UTXO view as expected. And we do this with this simple structure, the UTXO processing context. It's going to be like a per chain block we want to validate. This is going to be the processing context. It's going to have the ghost DAG data of this chain block, which is important in order to know who's blue and red, who's the selected parent. Blue and red are important for the rewards, the Coinbase rewards. It's worth mentioning here, some people may not know, in Kaspa, blocks don't pay themselves. They don't create the Coinbase transactions paying the reward for themselves. But the next chain block merging, a merge set is the one which creates a single Coinbase transaction for paying for all the merged blocks according to the address they encode in the Coinbase transactions of themselves. And consensus verifies that each chain block pays correctly, otherwise it wouldn't qualify as a valid UTXO chain block and would be rejected. And so every block in the system pays this Coinbase transaction to all the merge set, but only one of them counts, only the one who eventually becomes a chain block. So you might find a few parallel blocks, each paying for the previous round, but only one of the Coinbase transactions will count. Essentially forcing that each mine block gets its reward once exactly, and not more, not less. So you need the ghost DAG data, and then you have the multiset hash. This is a special hash, a rolling hash that gets updated with the UTXO set changes and can be used to create the UTXO commitment. It's just a much larger number. It has 6,000 bits. The merge set difference, accepted TXIDs, rewards, acceptance data. So this is a processing context meant to be filled by the calculate method and verified by this method. So I'll do it relatively fast. So we go, first of all, we start with the selected parent transactions. So the first block essentially is the UTXO view of my selected parent. Doesn't include his transactions. It only includes his past. And now me as a chain block looking at him, I take him first because he's exactly should be coherent to the UTXO view he has. So I first process his transactions, and they should all be valid. And then I add the remainder of the merge set, processing the merge set blocks in consensus ordered, which gives precedence to, if there's a conflicting transaction, this would dictate through consensus who exactly counts and who doesn't. But I first start from the selected parent, because selected parent transaction, I take its Coinbase transaction and I apply it to the UTXO set. So my selected parent pays its merge set, and we apply the Coinbase transaction and the next chain block to the UTXO set. Essentially, virtual would apply the sync, the UTXO, the Coinbase transaction from the sync block as part of its execution. It's worth mentioning that the UTXO processing context can be not necessarily is always a real block. It can also be the virtual block. There's nothing here that can't be created for the virtual block also. So we have the Coinbase transaction. We already know it's validated because our selected parent by design is already known to be UTXO valid. So it's already validated. So we just take it and we apply it. We apply it to the merge set diff. We have a specific diff. So we start from the UTXO view of our selected parent, and then we accumulate the merge set UTXO diff. And we apply the validated Coinbase, and we apply it to the multiset hash, which will be used to create the UTXO commitment. And then we go over the just complicated code saying that we go through the merge set, starting from the selected parent. Now, here's a place where you see the usage of compose. We take the selected parent UTXO view, which itself is a composition usually. It's usually represented by, it's usually already the UTXO, the DB, and the accumulated diff we saw before. And now we add a merge set difference to it. So it's a composed view. It gets updated through the loop. It gets updated with information from the previously processed block by consensus order. So we're kind of processing the next block with the previous block already taken into consideration, which is where a double spend will be rejected, exactly because of this diff that already removed some specific UTXO. And now if we meet a new transaction, which is a conflict, this view will reject it. That's why it will not be accepted. do some kind of optimization here. We don't need to validate transactions from the selected parents completely because they already are, as we'll see. We accumulate, so we're inside a block. So we start accumulating the fee. We start validating the transactions. Validate transactions in parallel. Returns like a vector of validated transactions. It's not going to include any rejected transactions. Simply going to ignore them. Because this block we're looking at now is part of the merge block. It might not be a block that ever was a chain candidate. It might not be a valid UTXO set block. We're just looking at it, at the transactions, like I mentioned, like in the example. It might be this block down low here. So we're simply looking at it, at the transactions it has. And we're trying to validate them. So if some of them are not validated because they don't have an unexisting UTXO, so they're rejected. If the signature is invalid, they'll be rejected. So essentially, this returns exactly those who are valid by filtering. And we apply them to the diff, we apply them to the multiset, we add them as accepted, and we compute, and we use the calculated fee as part of the block fee. And then we save some acceptance data, which is used mostly for RPC purposes, like what transactions did this chain block accept. We keep track of the merge set rewards. This merge block now will get some subsidy, some fee. Subsidy is like the Coinbase reward. The fees, it is his public key. Okay, so that's the calculating the UTXO state of the block. Note that we didn't touch the transactions of this block. As I said, it might be virtual, might not have transactions. So we're not looking at the transactions of this block. And nothing, we didn't look at all at anything yet related to this header even. We just computed the UTXO state, which is reflected inside the UTXO, the merge set diff. And we accumulated the multiset hash, which will be used to create a UTXO commitment or to verify one. And we accumulated information of how to pay block rewards. Then the next function is to verify that the current block fully respects its own UTXO view. So we need the block header has to have the expected UTXO commitment according to the UTXO view we computed. We need the block header to have the expected accepted ID Merkle root, the block Coinbase transaction to reward properly, and in order to become UTXO state valid, we need all non-Coinbase transactions, all normal transactions, to be valid against this block UTXO view, because we want to make sure that you were consistent with your worldview. If you included transactions which are illegal, we don't accept you as a UTXO valid chain block. Obviously, all blocks mined in Kaspa are valid also in terms of UTXO, because that's how consensus will build them. But if someone deviates, this is where it's going to be caught, and specifically his block will be disqualified from being a chain block. So just fast through this, we have the multiset hash from the context we just computed, and we finalize it, meaning we turn it into a shorter hash, and we verify it matches the header UTXO commitment. We verify the Merkle root, accepted ID. And we verify the Coinbase transaction according to the merge set rewards we computed. And we go over all transactions. We apply like the current UTXO view would be now the select parent UTXO view composed with the merge set diff. And we validate all transactions in parallel, and we make sure that no one is missing. They're all okay. And that's like, once a block passes this function, it's declared as UTXO valid.
Mm-hmm.
What do you think?
I missed the reward part, the block reward. Can you show it again?
Like what part? The how
it was in the end of the calculate coin.
Yeah. So when we go through the merge set, the merge block, we accumulate the block fee. Okay.
Mm-hmm.
For each accepted transaction, we have the fee, and then we simply we keep this in memory. Like we have merge set rewards, like a hash map to the merge block,
Mm-hmm.
to the block reward. We keep it separately for now. Like we keep the subsidy. Which we don't compute here, like the reward, the block reward, because it's already given from the block structure, which was verified in previous like pipeline stations. So we don't go to the Coinbase manager and like ask we don't verify the subsidy. We consider it as correct, and we accumulate the fee and the scriptable key. That's all you need later to compose. And later we take this, we verify the Coinbase transaction. We take the first transaction of the block, and we use this information to compose what the expected Coinbase transaction looks like, and we verify they're the same.
Mm-hmm.
So we can go into this, but I don't think you can.
No, it's okay.
Can look at it offline also.
It's too much detail
here.
Mm-hmm. Okay.
Yeah. I don't know like how much. So this is like, okay, I'll just go over it fast. So this function is like a utility function where you can think of it as like a black box. This tries to move the UTXO state. This is like not easy to understand part, but if you try to do this in Go, I wish you luck. Here it's like the most pure form of it, I think. So you get like a from. We want you to try and perform the reorg from to to. And you get a diff, and you should update the diff as you walk through from to to. Mm-hmm. At some point, you might end up at a block in the middle of the way, and like let's say the selected parent of 2 is valid, and then 2 wasn't. So in this case, you will return the selected parent of 2. Like the only thing the consistency requirement from this function is to have the diff be the diff of virtual from the hash returned. So this is more like a subcomponent now. Think of it about it as a subcomponent where you try and move along this reorg. Okay, we're trying to get from V from S and this image to the new S. Okay, so here we're gonna go like walk down a chain and gonna walk back up. So you can see, I don't know if this is familiar, but we have a backward chain iterator, which you can traverse now. And you know these are valid, and you know because these are, you're starting from a chain block, which was already UTXO valid. So you know it has a UTXO diff in the store and a merge. You know it has this. So essentially you go back to the chain and you apply the diff in reverse to the diff.
Perfect.
That's the rolling back. Mm-hmm. That's the rolling back. And then we got to the split point. Meaning we got to this, we found the split point would be a mutual chain ancestor of current and 2. Because we start from, we go down a chain, And we're looking for a chain block, which is also a chain ancestor of 2. So that's the split point, so that's where we stop. That's our current diff point, and then we go back up with a forward chain iterator. Forward chain iterator, unlike the backward chain iterator, needs, like if you notice, backward chain iterator only needs from, because you can go back without knowing where you're going, right? You just go over the selected parent links. But going back up, you need to know to what direction. You want to walk from the split point back up to 2. So you look amongst split point children, and you find the child which has 2 on its chain, which is on the chain of 2. So it's there's an efficient way to do this with our reachability algorithm. It's like a binary search over the children. So that's how we have a forward chain iterator. Because think about the chain structure as a tree. So if you go from the leaves to the root, you know exactly where to go. But if you go from the root, so you need someone guiding you to what leaf.
Exactly.
Yeah, so that's the walk up. And now we walk up, and now we don't know if this was already UTXO verified or no. So we check the UTXO diff store. If we already have a diff for this block, it's a well-known sign that it was UTXO valid and has already stored the UTXO diff. So we simply apply the diff in place, this time without a reverse. Like here we use the reverse, and here we don't need a reverse because we're going back up. And if it's not, we compute it. So this is where along the way, we kind of keep track of like our diff is going to be updated. Is already our diff is always updated to the selected parent of where we are now. Because as you see, if we're valid, we update the diff. So eventually, the next forward chain block would be the block which has us as selected parent. So it's going to have the selected parent UTXO view. Is that clear?
Yes, I think so.
What I'm saying is that the selected parent UTXO view is a composition of the stored UTXO set with the diff, current diff, because we always kept updated. So it represents exactly our previous point, which was the parent of this block. Like in the first iteration, the split point, look, we have a split point, which is exactly where we had the split of the reorg, right? And now we walk the chain iterator from split point up, and we, if you look at this true, it means inclusive. It means no, but in any case, it doesn't include the split point itself. So the first block we're going to get from the iterator is the next one. So when you look at this block here, you'll notice that diff represents exactly the UTXO's view of that previous block. So essentially this holds. So we can now create a processing context, and we can verify this block. We can calculate the UTXO state with this UTXO view, and then verify it. That's the functions we know.
Okay.
If there's some kind of rule error, the block is disqualified. Otherwise, we take it and accumulate the diff we just created, the Mergeset diff, and we move on.
Okay.
Once we verified the UTXO state is correct, we also commit it to the database. The Mergeset diff, like that's what we queried here. So that's the process. So this is like the way to move UTXO state relatively from one point to another. And the think search algorithm essentially does this over and over until it succeeds. and it must do this because it can encounter disqualification and stuff like that. So this is complicated to comprehend, I think, but essentially it goes through a heap which is sorted by decreasing blue work. So these are like the candidates to being the sink. And if you disqualify some kind of tip, you actually enqueue its parents because they might have sufficient blue work and might be the next sink, and they might have a valid UTXO state. So you search through this heap, updating it as you go. You call this UTXO state relatively function, and once you get a match, you simply return it, more or less. This is where you detect finality violations, or here it's sort of like the parents of a block, if it wasn't qualified. So that's the sync search. It's amazing we still have 37 people on the call. Okay, let's look at this for a second now. So yeah, I don't think we can look at build block template. Okay, sanity check for number 1. Get return address or input amounts of a recent transaction. Think about it from the I just get a transaction that was accepted by the DAG, right? I'm an LPC client and I'm tracking accepted transactions, and I get this event of a chain block, a new update to the chain, and it has a set of accepted transactions, and I have them. But even if I have the block DAG data, so I have these transactions, but they don't have, as I showed before, a transaction object doesn't hold the inputs. It just holds this weird key, right? It doesn't hold the actual input value or the address. So, and if I look at the node now, this transaction was accepted, right? So the UTXOs that spent are no longer in the UTXO set.
Exactly.
So how can I get them? What do you think? Where's Coder? He ran away. He knows the answer.
he went away. From the Mempool perspective.
When Anton brought this up, I was thinking, where is this information? And the node knew this 10 seconds ago, right? Because this transaction was just accepted. The node must have verified the amounts and the signature. So the node knew this. It can't be that something the node knew 10 seconds ago the node has to have a way to roll back.
So
what's the mechanism for rolling back?
We have them in this UTXO diff.
Right. Exactly. So the answer was, you just got an accepted transaction, right? And you know which block accepted it. You have an accepting block hash. So if you give us the accepting block hash and a transaction ID, we can go to the node DB and look at the UTXO diff of that chain block. And the removed entries must include these.
Exactly, it must include this transaction.
Yeah. While I was thinking about this, by the way, if Coder is not here, so he's like, I noticed like he implemented recently this functionality. There's like a pull request, and I think I noticed like a slight like in some weird cases the removed entry will not be in the UTXO diff. You know when?
If the parent, if there was too many tips.
No. this was the accepting block hash, so it must have accepted this transaction.
Oh, yes.
So supposedly it must have the UTXO it's spent in the removed part of the UTXO diff. But there is an exception, a rare case where, think about the case where the merge set has two blocks, one after the other, and one of them, and a chain of two transactions, one spending the other. So this merge set had a transaction creating UTXO, and it was spent within this merge set. So the merge set diff will not have this UTXO specifically, because it's not part of the difference. It was created and spent. It's not part of the difference.
Oh, of course. Yes. Okay, I see.
So it's kind of, so in this case, obviously the transaction where we came from is around. So we can extract the UTXO from that transaction. Like it's a rare case, but it has to be the case that this first chain transaction was in the merge set in the blocks, so we can find it, and that has the information of the UTXO entry it created. Think about it, but that's like the okay.
I have to think about it a bit. It's a lot of information at once.
Yeah. Okay, I'm going to get back to the mempool gap in a moment. I first want to mention the peer-to-peer and fast relay. Hopefully I think we're losing a listener by the minute. Oh, we're close to the end. Okay, I wanted to. So relay I'm jumping now to peer-to-peer logic. And we have this interesting phenomena. So essentially, hard to understand, but we send the block to processing in consensus somewhere here. And then we get two tasks. Like these are like, if you know Rust, so these are special objects which can be awaited on, meaning asynchronously waited on. So we get notified like this. Await means we're going to get notified once this block task is done. We return two different tasks, one indicating that header and body block processing was done, and another one indicating that this block was taken into account to virtual state already. And the cool part is that we can broadcast the block without the virtual, without UTXO state processing of it yet, because we consider blocks valid as soon as they pass the two first validation stations. We can actually already start broadcasting this block to others following the block task. We don't need to wait for the virtual state task. Now, this is important because, like we noticed, like the block task has fine granularity, meaning it once this block completes, it's done. Virtual state is more like an operator that acts. Virtual state is an operator that that act on a bunch of blocks, right? So it can be like, it can take a little more time. It can take, maybe it can process 10 blocks or 20. And you'll get this task finished with like less granularity. It can take a second or 500 milliseconds. So avoiding the need to wait for this task to finish and already broadcasting significantly is important to the health of the peer-to-peer network and the fact that the DAG is propagated as fast as possible, and we reduce what we call the computation latency. Because think about it, if there's a half a second delay on each peer-to-peer node before it broadcasts, so this accumulates to a few hops in the peer-to-peer network, and this so hopefully this one works live. Yeah, it does.
It does.
The fact that this is the fact that this is a nice structure, and you see essentially that even though it's on 10 bps, it's relatively narrow, is related to that line of code where we broadcast faster.
Mm-hmm. Before waiting
by the way,
for the virtual to complete.
Yeah, this is the backing node. Okay, so that's sanity test number 2. So the mempool gap is the last thing I'll touch, and you know about it. So essentially, we learned, maybe it's not so much of a sanity check, but we learned that virtual, we need, again, I don't know what's the best picture to use. Okay, I'll draw one fast. Okay.
Which point are you willing to discuss? The last one?
The mempool gap.
The mempool gap.
The mempool gap.
Okay.
Yeah. So assume we have many tips.
Mm-hmm.
And assume that a block can only point at four parents, for instance. Not the real number. I'm just for this. So this is gonna be like 1 second. This is gonna be like the sink. And then so sink is always pointed at, and then we have 4 other blocks. So the merge set of virtual includes 3 other blocks. And I'm ignoring all the history. But it's not looking at 5 more blocks, right? So the UTXO set of the database already has the UTXOs, which are the outputs of the new transactions in these 3 blocks. But it doesn't have, the UTXO state didn't take into account yet the other blocks. So what does the mempool do in this case? We didn't speak about build block template, but I think it can still be understood that the mempool doesn't want to mine if there's a transaction inside here, and it's still in the mempool. So even though it's not in the past of virtual, we still don't want to mine it into the next block because someone else already mined it, right?
Yes.
I don't want to go into greedy people who want to compete on a high fee transaction. I'm not speaking about such people. So essentially, this transaction was already mined, and I'm a decent miner, and I also don't know if even if I try, I'm not necessarily proceed that transaction because it's already known. So essentially, I don't want to mine transactions seen in that block, but I still don't have them counted to in the UTXO set view, right? So I have this transaction, and I already have it in the mempool. This is the mempool. And exactly now, this annoying user sent a new transaction which depends on this transaction. So what happens now, so the logic of the mempool is to first try and, if you find the transaction 1 depends on transaction 2, you try and take the UTXO from it. And if you don't find the UTXO in the mempool, you look at the consensus UTXO set.
Yes.
So here, our problem is that once we see the transaction is included in block B, we already remove it from the mempool. So we
but it's not
remove it here. But it's not counted in the UTXO view because virtual doesn't look at this block yet. So what happens is a rare bug where the user's wallet submitting transaction 1 is going to get an error saying it's an orphan. And if it waits a second, virtual is going to point at B in a second for other blocks, and it's going to be valid. But there's a point of time that because of this gap between the mempool and consensus, we get to this rare edge case. So we had this user, someone testing on testnet 11, reported this a few days ago when the net the DAG was wide.
Mm-hmm.
And he had the script running and sending transactions every few seconds. So he had this every now and then.
It was every 5 seconds, and you just suggested to extend to 10 seconds. Every 10 seconds.
So my thinking is that if you do it every 10 seconds, it's probably already going to converge, and you're not going to see this phenomenon.
Mm-hmm.
So the solution is something we need to design yet.
Mm-hmm.
Still design. One straightforward option is to keep these transactions in the mempool, but mark them as not to be mined. So they are going to provide the UTXOs for the supposedly orphan transaction, but not mined. But yeah, now you have the full picture more, I think, hopefully.
No, it's clear.
Yeah.
But can we extract this information from the consensus?
So we get the fact that the transaction is included into a block. We get through we see the new block, right?
I mean,
the question is when do we remove it? That's what you're asking.
Mm-hmm, exactly.
So it seems like we need to track also acceptance, but then you need to count for. So it gets complicated. Yeah, I agree. Okay.
We will find a solution, I'm sure.
Okay. So I'm going to look now at the question.
Coder is coming back, I think.
While he's typing, let's embarrass him. Give a message to new devs who want to get into this. Do they want to get into this? I'm not giving copyright on that, mem. Trust me. Yeah, we can talk about RBF, but maybe George wants to go to sleep.
Well, I'm feeling.
If you take the micro, you take the.
I didn't hear you. What did you say?
Actually, no. I think it's too long.
Yes. Just the status replaced by fee.
Okay, so I'm gonna stop sharing my screen.
Okay, so yes, we just designed a solution that allows to.
I couldn't hear.
Oh, so maybe my bandwidth is bad.
For me, it's getting late, so I don't mind getting off if you want to speak about it or Aspect wants to go on.
No, but I don't want to go into too much detail. It's just we have a solution.
Okay, I think it was a long enough conversation. I don't think.
Yes. Okay. Let's keep that for a next meeting or whatever. Fine.
Okay. So we should wrap up. Anyone?
Yes, I think so. If anyone has a question, it's the last chance to ask. Yeah,
I'm looking at the chat. If anyone wants to ask something, thank you for joining. Thank you for being with us. Watch again, hopefully.
Yes, definitely.
I hope this was valuable.
It's very dense, so it's not an easy topic.
To me, if this went well, and I'd like to get sincere feedback later, I probably do spontaneous such meetings often, like once a week or once in 2 weeks. Just go into some area of the code, gives a background, one slide, drawings, and like can be. I can name like 10 parts of the system which are worth a session. Maybe a little shorter than this, maybe not.
Okay, Michael, thank you very much. And let's do it again.
Yeah, thank you so much for doing your part so nicely and being the one who has to answer hard riddles online.
Yes.
Next time, Aspect is doing your job. I don't know why.
You will enjoy it, I'm sure. Okay.
Okay. So, thank you everyone for joining. See you. Bye.
See you.